Here is the problem. We have a conical funnel, like an inverted cone. Water flows in from the top with flow rate Q in and flows out through a small opening at the bottom with flow rate Q out. The height of the water level is h, measured from the bottom opening. The cone has a 45-degree half angle, which means the radius at any height equals the height itself, r equals h. The outflow depends on the opening area A and the water level. Q out equals A times the square root of 2gh. Part A asks, what are the input and output signals? The input is Q in, the flow we can control. The output is H, the water level we want to observe. Part B. Let us derive the state equations. Because of the 45-degree angle, the radius at height h equals h. The water surface area is A equals pi r squared, which is pi h squared. The water volume is V equals 1/3 AH, which gives pi h cubed divided by 3. Now apply mass balance. The rate of change of volume equals inflow minus outflow. dV dt equals Q in minus Q out. Taking the derivative of V, dV dt equals pi h squared times h dot. So pi h squared times h dot equals Q in minus A times the square root of 2gh. Solving for h dot equals Q in divided by pi h squared minus A times the square root of 2g divided by pi h to the power 3/2. Using the normalized version where A times the square root of 2g equals 1, with state x equals h and input u equals q in, we get x dot equals u divided by pi x squared minus 1 divided by pi x to the power 3/2. And y equals x. Part C. Linearize around x set point equals 1. First, we need to find u set point from the equilibrium condition x dot equals 0. Setting x dot to 0. U set point divided by pi times 1 squared minus 1 divided by pi times 1 to the power 3/2 equals 0. This simplifies to u set point over pi minus 1/pi equals 0. Therefore, u set point equals 1. Our set point is x equals 1 and u equals 1. Now compute the Jacobian. The state function is f of xu equals u divided by pi x squared minus 1 divided by pi x to the 3/2. The partial derivative of f with respect to x. From the first term, we get negative 2u divided by pi x cubed. From the second term, we get positive 3 divided by 2 pi x to the 5/2. At x equals 1, u equals 1. Negative 2/pi plus 3/2 pi. Finding a common denominator. Negative 4/2 pi plus 3/2 pi equals negative 1/2 pi. The partial derivative of f with respect to u equals 1 divided by pi x squared. At the set point, 1/pi. For the output y equals x, partial g partial x equals 1 and partial g partial u equals 0. Putting it all together, the linearized state space model is delta x dot equals negative 1/2 pi times delta x plus 1/pi times delta u. Delta y equals delta x. In the standard ABCD form, A equals negative 1/2 pi, which is approximately negative 0.159. B equals 1/pi, approximately 0.318. C equals 1 and D equals 0. Notice that A is negative, meaning the system is locally stable around this set point. If the water level is slightly above equilibrium, the increased outflow brings it back down. The time constant is 2 pi, about 6.3 seconds. Let us recap. We modeled a conical funnel with a 45-degree half angle. The key geometric insight. R equals h gives A equals pi h squared and V equals pi h cubed over 3. The mass balance gave us a nonlinear state equation with x to the negative 2 and x to the negative 3 over 2 terms. We found the set point u equals 1 from the equilibrium condition. Linearizing at x equals 1, u equals 1, we got delta x dot equals negative 1 over 2 pi delta x plus 1 over pi delta u. The negative sign in A means the system is locally stable. 3 parts, 1 complete funnel analysis. Done.